How's it going, folks? Today we are going to be looking at section 8.5 using exponential and logarithmic functions. So today's goals, we're going to be able to write and solve exponential growth equations and inequalities. We're also going to be able to write and solve exponential decay problems. So we're going to talk about using logs to solve exponential growth problems. So the continuous exponential growth equation is often used to represent population growth and is the same as continuously compounded interest formula. So just both of these are essentially saying we're working with the same thing. They're very, very similar. So in this first example here, we're going to talk about continuous exponential growth. In 2016, the population of Florida was 20.61 million people. In 2000, it was 15.98 million. We want to write an exponential growth equation. So using our exponential growth equation, which is going to be this top one here, we're going to have y equals a e to the k t. Now we're going to know a couple things here. We're going to know that y is our output. Well, our output, we need to solve for a couple of these variables. So a is going to represent our starting value, which is going to be 15.98. This is going to be our starting value. Let's call this year 0 instead of year 2000. So we've got y equals 15.98 times e to the k t. Now, big thing here, we don't know what k is. So we're actually going to need to substitute a value in to solve for k. So let's go ahead and use the function or the point 16, 20.61. So we have the point 16, 20.61. And we're going to substitute that in where 20.61 is equal to 15.98 times e to the k times 16. Okay, that's going to be, and we're going to go and solve this for k. So what we're going to do is we're going to divide by 15.98. I got 20.61 divided by 15.98. This is going to be equal to e to the 16k. And then since we're working with e, let's actually give both sides a natural log. So I can take the natural log of 20.61 over 15.98. And then we're going to take this as the natural log of e to the 16k. Now, anytime we have an exponent within a log, we can bring that forward and then multiply. So we've got the natural log of 20.61 over 15.98 equals 16k times the natural log of e. Well, the natural log of e is just 1, so we can just get rid of that, and we're going to divide by k. So, or divide by 16 to get k. So our natural log of 20.61 over 15.98, that's all inside the natural log, divided by 16 is equal to k. So we're going to get that k when we plug that in our calculator is 0.0159. So our general function will be y equals 15.98 times e to the 0.0159 t. That right there is going to be our exponential growth equation given that situation. Now, we're going to want to predict when the population will reach 25 million. So when y will be 25. So we want 25 to be equal to our general function here. We've got 15.98 e to the 0.0159 t. Let's go and divide both sides by 15.98. I got 25 divided by 15.98 equals e to the 0.0159 t. Let's give both sides a natural log. Our natural log of 25 over 15.98 is going to be equal to 0.0159 t times the natural log of e. I skipped a step there. I gave both of these a natural log. And since I have this to the power, I can go ahead and bring this exponent down just like I did right here. So from here, we're going to go ahead and divide by 0.0159 because the natural log of e is just 1, so we can get rid of that. So I'm left with the natural log of 25 divided by 15.98 divided by 0.0159 will be equal to t. That is going to simplify to be 28.14 years. So in 2028, the population will reach 25 million. Okay, let's jump to our last page of these notes. Okay, so for our check, an experiment starts with 20 bacteria cells. After 45 minutes, there are 710 bacteria cells. We want to write an equation that models the number of bacteria cells y after t minutes, and we're going to round to the nearest value of k to the nearest thousandth. So we've got that y equals our starting value, which is 20 e to the kt. Let's use our point 45, 710. So we get that 710 equals 20 times e to the k times 45. And then let's divide by 20. So I get 710 divided by 20 equals e to the 45k. And let's give both sides a natural log. So I've got the natural log of 710 over 20 equals the natural log of e to the 45k. Let's bring this 45k down. I've got the natural log of 710 over 20 equals 45k times the natural log of e, which is just 1. We can get rid of that. Let's divide by 45. The natural log of 710 over 20 divided by 45 will be equal to k, and that will go ahead and be 0.079 tenths, hundredths, thousandths. Perfect. So our general function here will be y equals 20 e to the 0.079 t. And then we want to find out after how many minutes the bacteria will have 1,000 cells. Let's set y equal to 1,000. Will be 20 e to the 0.079 t. Let's go ahead and divide by 20. Divide by 20, we're left with 50 equals e to the 0.079 t. Let's take a natural log of both sides. So I'm left with the natural log of 50 equals the natural log of e to the 0.079 t. Bring that down. We've got the natural log of 50 equals 0.079 t times the natural log of e. That's just 1, so that goes away. Let's divide by 0.79. The natural log of 50 divided by 0.079 will be equal to t. So we get that t in this case will be 49 point, see nearest tenth, so 3 minutes. Okay, so our last example of the day, we're going to use logs to solve exponential decay problems. So exponential decay can be modeled by this function given here, f of x equals a e to the negative kt, where a is our initial value, t is our time in years, or any kind of time value, and k is a positive constant representing the rate of continuous decay. So for our first one, the half-life, meaning that's the amount of time it takes for half of the atoms to disintegrate. The radioactive substance, thorium-230, is used to determine ages of cave formations of coral. So the half-life of thorium-230 is going to be 75,381 years. So essentially what that means is after this long, half of the original substance is going to be gone. So let's go ahead and determine our value of k and create the equation. So we know that f of x, or y, equals a e to the negative kt. Well, our a value is going to go ahead and be anything we want. I'm going to go and let a be just 1, because we know that after 75,381 years, it's going to be half of that. So I'm going to let a be 1, and let's go ahead and use our secondary point to solve for k. So if a is 1, we're going to let e to the negative k times that big number, 75,387. Let's go ahead and take a natural log of both sides. So I've got the natural log of 1/2 equals the natural log of e to the negative k times 75387. Let's bring that down so I get my natural log of 1/2 equals negative k times 75387 times the natural log of e. Again, natural log of e is just 1, so that goes away. Let's divide by negative 75387. So the natural log of 1/2 divided by negative 75387 is going to be equal to our value of k. That right there is going to simplify to be 0.12345 zeros, 9195. So our general function will be y is equal to a times e to the negative 0.0000, one more 0, 9195 t. Yes, it's definitely a little bit ugly there, but that's okay. That's going to be our general function where a is going to be whatever starting value we want it to be. Let's go ahead and look at this one here. So how much of a 2-gram sample, so that's going to be our starting point, should be left after 1,500 years? So we're going to get y is equal to 2 times e to negative 0.123459195 by 1,500. We're going to substitute that into our calculator, and we're going to get 1.973 grams. All right, folks, that's all I have for today. Thank you very much.